We're given a random variable x and it follows a binomial distribution, n is the number of events, and p is the probability of success. P is between 0 and 1, and we're told the mode of x is m. So this is what makes this question a little bit different to your standard binomial questions. You never really talk about the mode dealing with a binomial distribution. But don't forget, if you were to draw a binomial distribution, it actually looks a bit like this. Okay, I've purposely kind of not made it symmetrical, but it could be symmetrical if p was 0.5. Now, the thing is, and it even talked about this in part C, sometimes you get two modes. You can never get three, but it is possible that it will look like that. And that's something we kind of need to take into account even in part B. But first of all, write down in terms of m, n, and p an expression for the probability that x is equal to m. So this is just actually a standard probability. It means we've got m successes. So remember there are n events, and then I divide by m factorial, n minus m factorial. Let me just briefly talk about that. So I've got success, 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 so on, m times, and then all the rest are failures. Because I've got n in total, it must be that this is n minus m. And now this is a permutation problem. Essentially, I am arranging n objects, and so there are n factorial ways of doing that. However, m of them are the same, so that's why I need to divide by m factorial, and another n minus n, m of them are the same. I'm going through this now because maybe you're doing this question and you didn't cover that when you did this topic, but I feel like it's quite important to understand where that comes from. It's all the different ways that you can arrange your successes and failures um, to have m successes. And once you've got it, like if we just want to work out this single probability, we would then times by p to the power of m. Because you're going along your tree diagram, p times p times p, you do it m times. And then it's 1 minus p, that's the probability of failure, to power n minus m. So that is the answer to part A. I looked at the mark scheme and it will accept you just writing NCM in different notations, but I've written in factorial notation. Okay. B, this is the hardest bit of the question by far, but C relies on it. So it says, determine in terms of n and p an interval of width 1 in which m lies. And this is what you have to do. You have to think about the fact that the probability that x is equal to m, right? Let's say it's this one here. That is going to be greater than the one after it. So we can write that it is greater than the probability that x equals m plus 1, the next one up. Except there could be a situation where we have two modes, and so they could technically equal one another. So technically speaking, we should put a greater or equal one sign in. But that is the absolutely crucial bit to this question. And if if you're watching this video, having been not sure where to start, this is where you start, okay? But there's still quite a lot to do. We're then later on going to look at the fact that the probability that x equals m is also greater or equal to the probability that x is equal to m minus 1. That's how we're going to get our interval, because it's going to be between these two values. Or sorry, it's not going to be between these two values. It's going to give us an interval. I'll show you in a sec. We've already got this, so just going to write it down. Remember, it was n factorial over m factorial n minus m factorial, p to the m, 1 minus p to the n minus m. And that is going to be greater or equal to n factorial over, for similar reasons, m plus 1 factorial and then it's going to be n minus m plus 1 in brackets. I can just make it minus 1 here, factorial. And I'm running out of space, so I'm going to be timesing by p to the m plus 1, and then 1 minus p to the n minus m minus 1. Again, I'm subtracting m plus 1 in a bracket, so I can just get rid of that bracket and write n minus m minus 1. You can see when I times these two together, I'm going to be left with n. So there's definitely n successes or failures involved. Okay, this looks pretty complicated, but we can cancel it down significantly. For example, we can just divide through by n factorial. Okay, get rid of that from both sides. That's the only common term exactly, but there's lots that are very similar. For example, we've got p to the m and p to the m plus 1. So this is just p to the m times p. So I can cancel that out with the m. And I can do similar over here. I've got 1 minus p to the n minus m minus 1. So I can cancel that out. There's just going to be 1 left over here. And before I do any more, let me just write my next line down then. So it's going to be 1 minus p to the m factorial. Right, I'm actually going to do a bit of sorting it out now. So n minus m factorial, let me just say like 9 factorial is actually the same as 9 times 8 factorial. I can just take the number and then I can times by the factorial of the number below it. So I can do the same over here. N minus m factorial is actually n minus m times n minus m minus 1 factorial. And you'll see why I did that in a minute. And that's going to be greater or equal to p. Remember, I've still got this p. And then similarly, I've got m plus 1 factorial, so that's going to be m plus 1 times n factorial. And then I've got n minus m minus 1 factorial. That's good because now I can cancel out the m factorials and this one here. And it's suddenly become a lot simpler. This will be positive and this will be positive, so I can just cross multiply. I'm going to get m plus 1 times 1 minus p is greater or equal to p times n minus m. Multiplying out these brackets will give m minus mp plus 1 minus p is greater or equal to pn minus pm. These are going to cancel. So I'm going to get m is greater or equal to pn plus p minus 1. Okay, I'm just going to bear this in mind for the moment. I will put a box around it. That's going to be pretty useful. It's not giving me an interval, but it's giving me at least, it's got to be greater or equal to this. It's like a lower bound, essentially. Right, so that came from this being greater than this. But we also need the fact that this is greater than when we put m minus 1 in there. And again, I can write down my inequality. I'm going to go straight back to factorials. You can take shortcuts, but I want to be really careful. What I mean is I can kind of look at the result here and maybe just modify it quickly, potentially, but I think it's safest to just write the whole thing out again. Okay, this time it's going to be n minus m plus 1 factorial. And I'm going to be timesing by p to the m minus 1, then 1 minus p to the n minus m plus 1. Okay, convince yourself that it's that. I'm not going to go into any more details. But in the same way, we can cancel things out. Cancel that with that. P to the n minus 1 I can cancel with this just to leave me p. This one will cancel with this just to leave me 1 minus p. Now this time I've got m minus 1 factorial, so it's actually I want to write my m factorial as m times m minus 1 factorial. And this one I'll write as n minus m plus 1 times, oh, I can fit it in, times n minus m factorial. And then this is going to cancel with this, and this is going to cancel with this. Cross multiply. And expand the brackets. And this gives m is less than or equal to np plus p, which gives us our upper bound essentially. Therefore, overall, we had that m was greater or equal to pn plus p minus 1. But that it's less than or equal to pn or np, doesn't really matter which way around I write it, plus p. And this gives an interval of width 1. I could factorize the p, but I think it's absolutely fine to leave it like that. Hey, I think that's quite tough. That's like this is one of these questions where this is the first sort of time in advanced extension award questions that we've been asked about statistics, and just to be thrown that when you probably never seen it in A level before is a challenge. But I hope it made sense. I hope you're happy with it now. We're then told to find a value of n where n is greater than 100 and the value of p where p is less than 0.2, for which x has two modes. I was talking a bit about that before, how we could possibly get that. And for our chosen value of n and p, state these two modes. So for this to be the case, got to look at this interval and try to get, you can see we know that the mode can be within an interval of 1. So I've got to find a situation where basically Pn plus P is a whole number. That's the aim. Because if Pn plus P is a whole number, then M is less than or equal to that, but it's also going to be greater or equal to 1 less than that number. And that's going to mean that it's both of them. So I'm going to tell you how I did this question. Like I didn't do it as efficiently as I could have, but if I just tell you the answer, then you might be like, oh, how did you know to do that? So I didn't choose the best possible option. I just said, all right, I'm going to let n equal 1,000 because that's like it's greater than 100, but it's like a quite a nice number to multiply by. And p equal 0.1 because that's also a nice number to multiply. So then np is going to be 100. And I'm going to get that 100, I'm just substituting now into my formula from above, plus 0.1 minus 1 is less than or equal to m, which is less than or equal to 100 plus 0.1. Now we're getting into, you can see actually this isn't going to work because I said we needed a whole number, but let's just roll with it. I'm going to get 99.1 is less than or equal to m, which is less than or equal to 100.1. So that didn't quite work, but it gave me what I should actually use instead, because I want them to be 99 and 100. Like that would be one thing that would work, and I can get that if I make instead of 100, if I get 99.9. So only one node here. In fact, it would be 100 because remember it always has to be a whole number. So instead, let n equal 999, and p can still be 0.1. So then np is 99.9. So now I'm going to get 99.9 plus 0.1. See, this is now going to be a whole number. And so is this. So this is not the only example. Okay, there's going to be lots, but basically you need to get the left-hand part a whole number and the right-hand part a whole number. So it's going to be 99 is less than or equal to m, less than or equal to 100. The two modes are 99 and 100.